In section 7, we're going to talk more about systemic blood pressure, which is really a key player in making sure we get the blood where it needs to go. So we began the blood flow with the pumping action of the heart. So every time your heart contracts, it's going to push blood into your arteries, and that's going to generate pressure. But blood doesn't just rush through without any resistance at all through a circulatory system. So as it moves through smaller and smaller vessels, resistance is going to build up and pressure is going to drop. So the highest pressure is right at the aorta, just as the blood is leaving the heart, and then it's going to gradually decrease as it travels throughout the system. And the steepest drop is actually going to happen in our arterioles. So arterial blood pressure is mainly influenced by two things. So the elasticity of the arteries near the heart, basically how stretchy are they, and the amount of blood being pumped into them at a given time. So near the heart, blood pressure isn't constant, it's pulsatile, meaning that it's going to rise and fall with each heartbeat. So when the left ventricle contracts and pushes blood into the aorta, we get what's called the systolic pressure. So this is the peak pressure in the arteries and usually about 120 millimeters of mercury in a healthy adult. When the heart relaxes between beats, that pressure is going to drop to its lowest point, which is called the diastolic pressure, typically around 80 millimeters of mercury. So the difference between the systolic and diastolic pressure is what's known as the pulse pressure. And you can actually feel this as your pulse. So that familiar thumping in your wrist or your neck is actually caused by the expansion and the recoil of arteries with each heartbeat. But to really know how blood is getting to your tissues, we have to look at something called the mean arterial pressure. It's not just the simple average of the systolic and diastolic pressures because your heart spends more time relaxing than it does contracting. So we have to calculate it like this, where mean arterial pressure is equal to your diastolic pressure plus 1/3 the pulse pressure. So for example, if your blood pressure is 120/80, then your mean arterial pressure, or MAP, is 80 plus 1/3 of 40, which equals about 93 millimeters of mercury. So that's the pressure actually pushing through the capillaries and feeding your organs. Both the pulse pressure and the mean arterial pressure are gradually going to drop the farther blood gets from the heart. So that by the time you reach the end of the arteries, the flow becomes non-pulsatile, meaning it smooths out into kind of like this steady stream. So in terms of checking your circulatory health, we use vital signs. So these are going to include pulse, blood pressure, respiratory rate, and body temperature. So when we take a pulse, we usually use the radial artery at the wrist, but there are other pressure points where arteries are close to the surface and places where you can press to either stop or slow down the blood flow, kind of like in the event of bleeding. Okay, blood pressure itself is usually measured with a cuff and a stethoscope. You'll be performing a blood pressure lab if you're taking this class fully face-to-face. And it uses a specific method. So I'm not going to go into this here because you're going to be doing either a virtual lab on this or a face-to-face lab where you can understand more about this. Okay, so now let's talk about capillaries. And again, this is where the real exchange is actually happening. So blood pressure is a lot lower here, starting around 35 millimeters of mercury and then dropping to about 17 millimeters of mercury. And that's a really good thing because high pressure could actually burst these capillary walls because remember, they're really, really thin. Plus, capillaries are really permeable. So even at a low pressure, fluids and nutrients can still be pushed out into the tissues. Okay, so finally, let's look at veins. So by the time the blood gets back to the venous system, the pressure is even lower because remember, it's dropping as it leaves the aorta. As it travels through the arteries to the arterioles, it's going to drop even more once it hits the capillary beds. to the point where what's the pressure of the blood that's actually entering into our veins is going to be 17 millimeters of mercury to 15 millimeters of mercury. So that's why our veins need help in order to get the blood back to our heart, especially when you have gravity fighting you along the way. So there are some things that can help that. And the three main helpers for venous return are going to be our muscular pump, respiratory pump, and sympathetic venoconstriction. So the muscular pump, when your skeletal muscles contract, like even when you're just walking, they're squeezing the veins and helping push the blood upward. And then remember we talked about one of the special adaptations, which were valves in the veins. So these valves make sure the blood doesn't flow backwards. The next one's going to be the respiratory pump. So when you breathe in, the pressure in your chest is going to drop and the pressure in your abdomen is going to rise, which is basically going to help suck the blood back towards your heart. And then finally, we have sympathetic venoconstriction. So when your sympathetic nervous system kicks in, like during exercise or in a stressful moment, your smooth muscles in your vein walls can contract, and that's going to also help push the blood back to your heart. So basically, again, just as this kind of a summary, because there was a lot of information in this section, blood starts with high pressure in the arteries and it loses pressure as it flows through smaller capillaries and then eventually into veins. Capillaries are going to operate at a really low pressure, and the reason for this is to help protect their structure and allow for their function, which is in gas exchange. Then our veins, they have really, really low pressure, so low that they actually rely on pumps and valves to help return the blood back to the heart.